Welcome to the second lecture on fault simulation. As discussed in the last day that our topic on fault simulation will be a 3-hour lecture. So, in the last discussion we have seen that to generate test patterns for a circuit for a given fault model like stacked fault model, what we have to do, there are two approaches. One approach was based on what you call that sensitize, propagate and justify approach. So, in that case given a fault, we first have to sensitize the fault, that is if these are stuck at one fault you have to apply a 1, you have to apply a 0, and if it is stuck at 0 fault then you have to apply a 1, then the value has to be propagated to some primary output, and then you have to justify the signal so that the values can be propagated and sensitized. So, then we have seen that this algorithm is bit complex, and if you want to apply it to all the faults present it will take a long time. Then we have tried to see for an alternative approach, in which case we say that rather what we do, we take a random pattern, we take one test pattern and then we apply in the circuit and then try to verify what are the number of faults that is detectable by this one. Then if there is, say, for a given random pattern, we can find out that around 70 to 60 or 20 faults have been detected, then we drop them and then we take another random pattern and try to do this procedure. So, what is the advantage of this procedure over the sensitize, propagate and justify approach? So, see, for example, the primary importance of this one was that in test pattern generation or any test pattern, there is a single pattern for multiple faults. In other words, a single test pattern can be applicable to test more than one kind of a fault. So, in this case what has happened? So, if you are using sensitize, propagate and justify approach, so one fault can be tested for a pattern, that is one pattern will be generated for the fault. But if you are using random patterns, then what happens? Multiple faults can be detected by a pattern that you can analyze and find out. That is, one random pattern is given, 3 or 4 or 10 or 15 faults it determines can be brought down, can be detected and can be found out that these are the patterns, this pattern can detect this and these faults. So, the problem of multiple fault detection is also taking into picture. But say for example, like say one pattern, say pattern I detects say 10 faults, fault 1, fault 2, fault 3. So, in sensitize, propagate and justify approach, the same pattern may be generated when you are trying to do this for all the faults F1, F2, F3 and Fn. But so you have to run the algorithm say 10 number of times. But if you see for a random pattern generation, when that pattern is applied and tested for which faults are being detected, then in the algorithm, the random test pattern generation algorithm, all the faults, that is F1, F2, F3, Fn, will be determined in one go or in a multiple number of goes, but for the same random pattern you will be able to find out that so many faults are detected. So, we are saved in two cases. First, the algorithm of random pattern generation is simple, and secondly also there is if the same pattern detects a more number of faults, then you do not have to run the algorithm repeatedly. Then we have seen that, so for some cases sensitization, random pattern generation is a much better approach than sensitize, propagate and justify. But I mean, this is not the end of the story, because we have seen that for if this one random pattern, applying a random pattern generates some new faults that are detectable, then you apply a next random pattern, then a few more number of faults get detected and so forth. But after some time, say around 90% of the fault coverage, so this saturates. So, after that what happens, if you apply a random pattern, no new fault will be detected and the procedure will keep on going till some 1 or 2 new faults will be detected and so forth. So, in that case the number of random patterns and determining whether a fault is detectable by it or not becomes more complex than sensitize, propagate and justify approach. So, we term them as difficult to test faults, and for those we better apply sensitize, propagate and justify approach. But for 90% of the cases, our random test pattern generation is a very good approach that we have seen in the last lecture. Then we have gone for that if you want to use random pattern generation or random test pattern generation procedure, then one very important part is that one, that there should be a procedure called fault simulation and circuit simulation. That is, given a pattern you have to find out what is the normal value of the circuit, that is the value of the circuit output without any fault, and then you have to find out what is the value of the circuit output with a fault. That is, you have to simulate this results. I mean, you have to simulate the circuit, because you do not have the hard copy of the circuit. And then if the output differs in the normal case vis-a-vis the faulty circuit, then we know that the fault is detected by the random pattern. So, fault simulation was a very important part of random test pattern generation, and we have seen that two types of fault simulation, one is event driven simulation and one is the simple compiled code simulation. And then we have seen that event driven simulation is very important, because it simulates only those part of the circuits where there are changes in the signals. Then we found out that then we have taken a very simple test pattern, what do you call, fault simulation approach, which is sequential or serial or sequential based kind of fault simulation, which we call the serial fault simulation, in which case one test pattern on for a random pattern you find out whether one fault is detectable or not, then you take another fault and find out whether it is detectable or not, and so forth. So, you take one by one fault at a time for each pattern, and then if the fault is detected by the pattern, you drop it, and so it proceeds. Then we find out that this is not very efficient, because for each fault in the worst case you have to simulate the fault n number of times if there is n number of random patterns are tried. So, now then we saw that there should be some improvement on this one, and then we told that from the next lecture onwards we will study some important other advanced fault simulation algorithms which will parallelize the effort, like which is in case of serial one fault at a time is considered to be checked that whether the fault is detectable by the random pattern. So, instead here what we will do, we will take one random pattern and then try to verify if more than one pattern more than one fault can be detectable, that is this verification that whether more than one fault is detectable by that random pattern is possible or not, that we are going to do. So, there are many algorithms like parallel fault simulation, then we are then slowly we will see there are some other algorithms. So, as the name suggests, first we will try with the parallel fault simulation, then deductive fault simulation is there and many others. So, we will see 3 more algorithms which are mainly towards the working on parallelizing the fault simulation approach. So, what is parallel fault simulation? As the name suggests, you can see parallel fault simulation actually can tell what is if for a given random pattern it can tell you which are the faults that can be detectable in one run of the circuit. So, one run of the circuit means one parallel simulation, one fault simulation of the circuit. So, what do you call a simulation of a circuit means you generally take some inputs and then you traverse to the output. This is actually you can say that I am scanning my circuit once, this is called the scan of a circuit. Okay. So, you are scanning the circuit once, and in one scan you can determine for a given random pattern more than one number of faults, that is parallelly you can parallelize your effort. You have to remember that in serial fault simulation only decision about only one fault can be done. So, how is it based? It actually uses a bit parallelism of a computer. So, let me just elaborate a very simple example. So, whatever if you see our computer, the hardware, there is a adder, multiplier, subtractor which is in our processor. So, whenever we execute some C program or any other programming language, inside the processor there is bitwise operation to finally do the operation, because we know that our computer is maybe a 32-bit machine or 64-bit machine, but generally in the processor level everything works at the bit level. So, if you add 3-bit numbers, say 110 and 111, then what happens basically that is actually this is this is 7 and this you know that is 6. So, if you do 6 plus 7 in a C language, basically what happens inside the processor, this is what is happening, binary it happens, and it is 1 plus 1 is 1, then 1 1 1 carry 1, then 1 and 1 remains, something like this. So, basically what happens, what I mean to say is that this hardware operation, this bitwise AND, bitwise OR whatever are happening by a hardware adder or a hardware multiplier or a hardware subtractor, whatever is available in your processor. So, there is a parallel bit, and we know that our machine is 32-bit machine or 64-bit machine. So, there is a 64-bit processor, so 64-bit ALU, so which may have a 62-bit adder, which may have a 62-bit ANDing operator, bitwise ANDing operator, 62-bit bitwise OR operator. So, all the hardware are available. So, parallel fault simulation actually takes what you can call takes advantage of this architecture of the machine. Say for example, I want to parallelize the output simulation, I want to parallelize the simulation of the circuit. The circuit is very simple as an AND gate, but what I want to do, I want to find out, I want to simulate the circuit for 3 inputs, one is 1 0, one is 1 1 and one is 0 0. So, if you take even if you take what you call the compiled code simulation, or even if you take a event driven simulation or whatever you do, basically then it will, if you run a simple C code. So, what will happen, first it will simulate for this one, then it will simulate for this one, and then it will simulate for this one. But if you can write a bitwise operation code, that is you know that I have to simulate for all, then what you can do, you can say that this is my first, these are my 1 bit input number, and for 3 bits are there, bit 1, bit 2, bit 3, because for 3 instances you have to simulate your circuit. So, what you can do, instead of writing a for loop and then simulating for 1 0 1 1 and then 0 0, you better represent it this as a number called 6. okay, and this one you represent as a number called 1 and you do bitwise AND. So, if you are doing a bitwise AND, immediately you will get the answer 0 1 0, which is nothing but 2. So, what happens inside your circuit, if whenever you are doing what you call bitwise this one and bitwise AND with 1 0 1, internally it can be done parallelly, because the internal hardware of your circuit or internal ANDing operation of your circuit, it can, if it is a 32 bit processor, it can support 32 bits parallelly. If it is a 64 bit machine, it can support 64 parallel bitwise operation. So, in this case, in one go your output will be something like 101 and you can get this 3 bit parallelly. In other words, what I am saying, so instead of giving 3 individual bits or 3 individual random patterns in 3 different goes, what we can do is that we can think that the 3 random inputs or n number of random inputs, you represent them as a vector, you represent them as a vector of binary numbers. And then, for example, if you are using a 4 numbers, for example, you have to simulate to find out the value of the circuit for 4 different inputs, then you have to write say 1 0 1 0 and this one may be 1 1 1 0 0, something like this. Then you represent this one as one vector and this one as one vector. Then what you do? Then you do a bitwise AND operation, then it will be done parallelly. Instead of first to simulate for 1 1 then 0 1 then 1 0 and 0 0, so it will be 4, but if you are representing these 4 inputs as in the 2 input cases as 1 1 as a vector of this size, 4 bit vector as binary numbers, and then you do bitwise operation, then it will be in a parallel, it can be done parallelly and in one scan of the circuit you can do it. Similarly, this is for the AND gate and this is for the OR gate, same thing you can do, but now instead of AND you do a bitwise OR operation. So, this is the basic idea of parallel fault simulation. So, generally what happens? So, if parallel fault simulation mainly depends on what is the parallel efficiency of your computer. So, if your computer is 32 bit machine, so you can do 32 bitwise operation parallelly. Then 32 minus 1, actually we will see how, then 31 faults can be simulated in one go. That is, we will see how. So, it is actually called we will see then input lines of any gate comprise binary words instead of single bits, and output is also a binary word of length w. That is what I was discussing. So, if your computer is having so what can be the maximum w, that means what it is saying that now instead of each random pattern, so what we are trying to do, we are representing the whole things as a binary vector. So, now what is the maximum length of the binary vector, like for example, as I told you, so in the last example we have seen 4 bits like 1 1 0 1 1 0 and 1 1. So, there are 4 numbers we have tried, this was one number, this was another number, this was one number, this was one number for simulating the circuit, but then we represent them as 2 vectors. So, here the length of each vector is 4. So, now the question is what is the length you can go? The answer is it is the length is maximum the bit length of your machine. So, that is what actually is called W, that is the bit word length, that is the W. So, output will also be a vector now instead of individual outputs, it will be again a vector. Now, if you call this W, what is the maximum length of W? The maximum length of W is the bit level parallelism or bit level parallelism supported by your computer architecture. That is also can be roughly said that if your machine is a 32 bit architecture, so it can go for 32 bit parallelism. And the output is determined by simple logical operation of of the individual bits, and actually this can be done parallelly because we know that bitwise parallelism is ever in our machine. Now, we will see that if W of a computer is say 32, then for fault simulation we can go only for 31 faults and 1 bit has to be reserved for normal operation, that we will see. So, that means if you know that if your computer is 32 bit machine, then what we can assume that in one go we can reason about not 32, but 1 less than that, we can reason only about 31 faults in one scan of the circuit. So, we will see this concept by an example, because the concept is otherwise bit listening directly from the theory, as I was mentioning, is not very helpful because it creates confusion. So, we will directly go on for an example and then we will see. So, for this let us assume that W is equal to 4 here, that is your machine is a 4 bit processor and only 4 bit numbers can be parallelly XORed, AND, ORed, NOT, etc. can be done only 4 bit at a time. So, this one, and as already discussed, so in case of if the machine in W is 4, then reasoning about only 3 faults can be done in one go, not more than that. So, how it is represented? So, what happens to the, let this be your circuit. So, we know that from our earlier discussion that each individual line like this one and this one, 3 fan outs, they are individual lines, like this one is one individual line, this one is one individual line and this one is one individual line. So, why there are individual lines? Because fan out lines will always be individual cases. Next what we are doing, so now what happens, and all the other nets obviously are individual lines. Now for corresponding to each individual line you should have an array. So what is the length of that array with a one dimension array? So what is the length of the array? The length of the array is W. So here is 4, so we have 4D arrays you can see at all the points of your nets of your circuit. Now each places or each box or each individual element of the array represents some special thing. So what is this? The first bit or the first box of your house array corresponds to normal performance of the circuit. That is, this is it tells the response, this array which corresponding to this net. So this place states that what is the value of this net. This place tells that what is the value of this net when there is no fault in the circuit. Next, there are 3 other boxes as I told you, because W is equal to 4 here. So, 3 can be used for fault simulation. So, there are 3 boxes here. So, each box corresponds to 3 different faults in the circuit. Say this one, the first box corresponds to I2 G1 stuck at 0. So, this one is I2 0, I2 G1 stuck at 0. So, this box corresponds to this fault. Next box is I2 OG2 stuck at 1. So, where is OG2? One minute, sorry, I2 G1, this is I2 G1 stuck at 0, okay, just a minute. So, this is I2, sorry, this one is OG2, sorry, this one is OG2. So, the next place, this one is for the OG2 stuck at 1 fault, this one is stuck at 1 fault, and I2, this one is I2, so this one is stuck at 0 fault. So, this place corresponds to this one. Now, this is for normal. So, this whenever this array is associated with line, first box implies that what is the value of this net when the circuit is normal. Then the second place tells, that is I2 G1, it corresponds to this fault. So, it states that what is the value of this line whenever this fault is there. Second, the third place tells for O2 stuck at 1 is for this fault. So, this net, this box for this array says that what is the value of this line whenever there is a fault over here. The study stuck at 1 fault, and the last box corresponds to stuck at 0 fault here. It also states that what is the value of this net whenever there is a stuck at 0 fault over here. So, and then again obviously as you can see there is an array at all the positions. So, for example, this array, what does it represent? This place of this array represents what is the value of this net when the circuit is normal. So, this box again states what is the value of this net whenever there is a stuck at 0 fault here. This box states that what is the value of this net, sorry, this net, not this one, this fan out net, whenever there is a stuck at 1 fault here. Similarly, last box states that what is the value of this net whenever there is a fault at this net. So, as you can see, so there is a what you call this is a one dimension array at each net in the circuit. So, the whole each this array at each point states what is the value of that net at normal condition, and each of the fault condition is represented parallelly. And you have also one point I have missed. So, we will start the fault simulation. So, with this representation we start. Then say for example, we give 1 1 at the input. That means, this is our random pattern here is 1 1 say. So, what is the random pattern? It is a 1 1. So, now for the random pattern 1 1, what is the value of this represents? This box represents what is the value of this net when the circuit is normal. As random pattern is 1, so obviously the value of this net is 1 at this point. So, the first box will have a 1. Second, for similarly for this net, so what is the value of this net when the input is 1 and the circuit is normal? The answer is 1. So, that is why these first 2 places in my array at I1 and I2 are 1 1. Now, let us see what happens. Now, let us the first box. The first box says that here in this case the first box say that what is the value of this net whenever there is a stuck at 0 fault here, okay, and input is 1 obviously random pattern. So, the stuck at 0 fault here has no effect on this line. So, obviously the answer will be 1 here, because if you apply a 1 over here, then if the stuck at 0 fault here, this line is free of fault. Similarly, the second box corresponds to this stuck at 1 fault. So, the stacket one stacket fault here has no effect at this net. So, the value will be 1 here, because 1 is applied at the input. Similarly, this stacket 0 fault has no effect here. So, the answer will be 1 in this case. So, this array will be, all values will be 1 1 1 1 here. Okay. Now, let us see for the second box. Now, this one will be already 1 we know. So, the circuit under normal condition, this net value is 1. So, it is 1. Now, you know that this stacket fault has no effect on this net, okay, no effect. So, the value will be a 1. Also, this stacket fault has no effect here. So, the answer will be 1. But now, the interesting thing is there, just see. Okay, so, now just see here, actually the answer should be 1, because we are applying a 1, but this blocks corresponds to this stacket 0 fault, this stacket 0 fault, and this stacket 0 fault has an effect at this line. So, this value will not be 1, but it will be a 0, which is shown here. So, these two boxes are unaffected, because this fault and this fault do not have any effect at this net, only this fault has an effect. So, what is we are going to observe, that instead of 1, this value will be a 0. So, this is how the input arrays have been filled up. Now, what we have to do? Now, we can easily see that these two values can be filled up, because fan out is just get propagated. So, this will be directly propagated here without any changes, because this net, okay, because this net, this is normal case, if this answer is 1, this value of this net is 1. So, it is done. So, this fault does not have any effect on this net. So, it is a 1. Same value is propagated from here. So, again this fault do not have any effect on this. So, this value is propagated here, and similarly also this fault, that is 0. So, this fault has an effect here. So, that means if there is a stacket 0 fault here, so this 1 gets 0 here, because the stacket 0 fault, which is also affected here at this net, sorry, this net is also affected because of the stacket fault. So, you get the answer a 0 over here. So, basically what happens, this box shows that if the input is 1, this input is 1, then under normal case this net is going to have 1, under this stacket fault the answer is 1, under this stacket fault the answer is 1, and under this stacket 0 fault the answer is 0. So, only you can see that this stacket 0 fault has an effect on this net, which is also obvious. So, this array becomes now 1 1 1 0. So, now in this case also, now when you are propagating this, so if you are having a 1 over here, so in the normal case this net is also going to be 1, correct, then this fault is having an effect on this one. So, this 0, this 1 gets converted to 0 over here, because if you are applying a 1 over here, so this is 1, because this fault is not having any effect here, but this stacket 0 fault is having a effect at this net. So, now in this 1 will not be propagated here, but it will be propagated as a 0, but this fault do not have any effect here. So, 1 will be remaining a 1, and this fault, this stacket 0 fault also has an effect at this net. Okay. So, this 0 remains a 0 over here. So, now this array will be 1 0 1 0 kind of a thing, right. Now, what you have to do? Now, again let us see what happens. So, just you have to know this is an OR gate, no sorry, a NOT gate. So, again you have to do a logical operation. So, as we know that we have a parallel logical operators are available over here. So, what you can do? So, logic NAND, logic NOT of this array. So, logic NAT should be equal to what? This is 0 0 0 and 1. So, this should have been the case here. You are inverting this, but you see that this is not a 0 over here. So, this is correct, but you see this 0 has been converted to 1. So, now why is that case? The case is so because it should have been 0, because by this parallel NAT operation this should have been a 0, but this net, this last house, the third house corresponds to this thing stacket 1, and this net, this fault has an effect on this net, and which is converting this 0 to a stacket 1 fault, and so the answer here will be a 1. So, you are going to get as a 0 0 1 1, which is the answer over here. So, this is a this thing has been converted, sorry, this is a mismatch, or what you can say is non-consistent. This one, it should have been a 0 by negation, but again this stacket fault is taking its role, stacket 1 fault is taking the role, and everything is getting changed over here, correct. So, now, so this is your array at this point, and now you can see again we can do a AND operation between these two. So, in this case it is 1 0 1 0. So, this and this base and this base you AND it, you will get 1 0 1 0, because there is no fault over here. So, no changes are there, and you get a consistent answer. So, it is 1 0 1 0, and this one is 0 0 1 1. Now, again you can do a AND operation here, again there is no fault at this area. So, there is no effect will be here. So, you can directly keep on doing the AND operation. So, you are going to get 0 0 1 0. So, it is this the case, only there will be only 1 1 here. So, it is the case. So, the final answer is 1 0 0 1. Now, so what happens, there is one interesting thing you have to observe, that we have gone only once from this part of the circuit to this part. First you have generated this array, then you have generated this array, then you have generated this array, and then you have generated this array. Then we have done a negation. Obviously, at each stage you have to find out if there is any effect of the stacked fault and the places of the array. Otherwise, you just simply do a AND operation, OR operation, NOT operation, whatever is the case, and then also here also you get the answer. This will be just a propagation, that is not a different, and then again you do AND operation. Now, you see we land, and in one iteration of the circuit or one scan of the circuit, we are able to complete our operation. That is very important. Now, you see what does this two arrays signify. So, in one scan of the circuit, we have generated these two arrays, say array 1 which is for this output and array number 2 which is for this output. Now, you see what happens, this is very important. See, this corresponds to normal. So, it says that if your input is 1 1, then the output at this net is 0 under the normal condition. And it says that if the input is 1 1, at this net the answer is 1. That is what it's saying. Then it says that the second place says that if the input is 1 1 and I2 G1 stuck at 0 and this stuck at 0 fault, the output of this net is 0. So, what it says that for random pattern 1 1 at this net and this fault, the outputs are same. So, this fault is not detected by the random pattern 1 1 through this net, because the input is similar. Similarly, for the last fault, that is your I2 stuck at 0. So, this being stuck at 0. So, what it says that for random pattern 1 1, the output at this net under normal condition is 0, as well as for this fault is also 0, the fault cannot be detected. But on the other hand, the third fault like O2 stuck at 1, this one, for the random pattern 1 1, here the output is 1 by this net, but for the normal case the answer is 0. So, this fault is detected by the random pattern 1 1 detected at this. So, that is what it signifies. But there is another output over here you have to see. So, in this case this is the normal point, and there is one point which is a difference. So, this is different from this one. So, this pattern, this output O1 detects, and this random pattern 1 1 detects this fault. So, one fault is detected. Now, again there is one more primary output you can see. So, in this case you see this is the output of the circuit at O2, when the random pattern is 1 1, it is 1, and there are two other faults, and in two faults which the output is different. This is similar. So, if it is similar, then at O2 this pattern cannot be detected, but this two fault is I2 G1, that is I2 G1 this pattern and this fault, and last one is I2 stuck at 0. These two faults are giving answer 0 0 when the input is 1 1 and the circuit and the normal condition is 1 at O2. So, this random pattern 1 1 detects this fault and this fault at O2 and this fault at O1 for the random pattern 1 1. So, this experiment or this algorithm, parallel algorithm, what it does, in one scan of the circuit, it determines that random pattern 1 1 detects this circuit, this stuck at one fault at this output, and this one at this output. So, what is the emphasis? In one iteration this is possible, but if you would have used normal random pattern generation procedure, then what you have to do? Then you have to do this 3 times or 3 scans of the circuits are required. So, one is for the normal, then you have to apply 1 1, then you have to simulate this fault, and then you have to find out whether this is different or this is different. One would be different, then you find out it is detected and the fault is dropped. Then again you fault simulate this circuit for this one and repeat it. Then again you fault simulate for this one and you repeat it. So, 3 times the circuit scanning is required, but here we did not require the 3 times of circuit scanning. We have gone only by one parallel procedure and we have got the answer. that is in one iteration we have got the answer that the 3 faults are detectable by the random pattern 1 1, and where it is detectable that also we have achieved. So, this is what is parallelizing your serial fault simulation algorithm. So, that is this algorithm is very efficient, but one thing you have to remember that if a circuit is having 200 faults, still you have to repeat the procedure, because you can parallelize only up to that limit at which you have the parallel bit array or parallelism supported by your processor. So, if your processor is 32-bit processing, parallel processing is possible, then you can parallelize up to 32 bits. So, 31 number of faults you can detect in one go. So, if you have 200 faults, then you have to repeat at least 200 by 31 upper ceiling. So, that many number of times you have to repeat the procedure, because here you are limited by the array size, and the array size is the maximum which you can have what you by called the parallelism which is supported on the procedure. So, again which you have discussed. So, this is represented in the array O2 is, this is the output, then that means what it says that O2 is 1 under normal condition, O2 is 0 under this fault, O2 is 1 under this fault, and O2 is this one. So, you can easily find out that these 2 faults are detected and this fault is not detected. What we have discussed, we are again writing showing in text. Similarly, for O1 this was the answer, this is the normal condition, and so you can see that there is only one point which is the different. So, this pattern, so pattern 1 1 at O1 detects only this thing correspond to this fault. So, this is the only fault which is detected, which you have already discussed. So, this is just again are rewriting in the text form. So, what we in summary what we have seen. So, we have seen that in fault simulation we parallelize or speed up your fault simulation procedure W by in W minus 1 time, if you consider W is the bitwise parallelism which is supported by your machine. So, what is the number of times you have to repeat? This is the total number of faults by W minus 1 iterations, again you have to take an upper ceiling. Okay. So, again if a new pattern is applied, so after that what you have to do? So, first you have to apply one random pattern, then you can try out your things for W minus 1 number of faults, and then again you have to repeat it how many number of times? Total number of faults by W minus 1 upper ceiling, and then when you have done this for all number of faults, that is for this value, then you can what you can do you can drop the faults which have been detected, and then again you take a new random pattern and repeat the whole procedure. This is also very simple, similar to serial fault simulation, but only thing is that in one go you can reason about W minus n number of faults. So, this is a parallelism you have obtained. But now you see what happens. So, if your computer is very good, you have a lot of parallelism possible, then your answer you can get it very quickly. But on the other hand, generally our modern computers or even a very fast computer, parallelisms are generally not more than 32 or 64 bit parallel bitwise operations are possible. So, now we will see another algorithm which is actually called deductive fault simulation, in which in one go we can reason about all the faults in the circuit, whether your computer has parallelism, whether your computer do not has parallelism, that does not matter that much. Bitwise parallelism does not matter. We will now handle it algorithmically, we will not handle it in the hardware level of it. So, the last this parallel fault simulation we have taken, what you can say is that hardware advantage we have taken, that is this processor has bitwise parallelism which can parallelize your efforts. So, that advantage has been taken by the parallel fault simulation algorithm. But now this is the new algorithm which we are going to study, that is the third fault simulation algorithm, in which case what we are doing, we are not going to look into the we are not going to make ourselves dependent on what you call the hardware of the computer, hardware architecture of the parallelism of our computer. Rather, we will make our algorithm in such a way that in one go you can reason about all the faults, that is our main first goal, and then we are not going to use parallelism and all those bit level parallelism, all those things into picture. So, that is our main goal. So, we are going to see in details about the deductive fault simulation. Okay. So, this is as I already told, deductible as the name suggests, that is it can determine in a single iteration about the detectability and undetectability about all faults in by one random pattern. That is, here you are going to apply one random pattern and then you are going to find out whether all faults are detectable by that or not. That is what is very important. So, in this case what is happened, the basic idea here is, so now what is the motivation in this case? They say that the circuit structure remains same for all the faulty circuits. That is, generally it does not happen that for a stuck-at fault 3 more AND gates have somehow come from the air and they are going to be regenerated, or because of some stuck-at 0 fault some of the AND gates will vanish. That is not going to happen. They say that the circuit structure remains same for all the faulty circuits. That is same in the idea means number of gates means or the looking of the structural identity of the circuit remains same. So, that is why they say that why we cannot find out an algorithm which can reason about all the faults at a time in one go, because if the structure of the circuit changes, then you have to go for the different iterations of the circuit. So, that is the basic philosophy, that why this excuse me, why people have thought that this idea should this algorithm or this idea should hold. So, let us see how it is going to happen. So, then what basic procedure will be, we will take a random pattern, determine idea about all the faults in the circuit, that which of the faults are detectable by that pattern and which are not, and then again which will be detected will be dropped, and then a new random pattern will be taken. So, even if your you have 10,000 faults in your circuit and your computer has 32-bit parallelism, but still your answer is going to be found out in only one iteration of the circuit. You need not go on 1000 or 10,000 mod w minus 1 upper ceiling. So, that also sorry in even if there is 10,000 faults, you can find out the solution in one go. You did not have to wait for this you did not have to go for this number of iteration. Now, what is the philosophy behind it? They say that multiple iterations should only be required if a circuit structure is going to change for different faults, but here if the structure is same, the same algorithm should hold. So, that is the idea of deductive fault simulation, and deductive, as the name suggests, is that you deduce about the faults which are detectable in one go for a random pattern. That is why the name called deductive fault simulation. So, what you do here, one thing you have to understand, we have taken a very simple circuit, this one, and first we have given this random pattern 0. So, if the random pattern I1 Z1, it will be 0 over here, 0 over here, 1 1, and OG3 output is 1. So, that is very simple. First a normal fault simulation is done. Now, we are going to see for a deductive fault simulation of the circuit. So, here one representation you should understand. So, if this line I am saying as I1, okay, so then I will represent L I1 is, that means it is the fault list of that net, and when we say that I1 underscore 1, that means what? It is detecting I1 stuck at 0. That is for any net, say net is named as I, then Li is the fault list, that is for that given random pattern, which is the fault that is being detected at that line. So, that is Li. Now, that is faults detected at I net by a random pattern, and then if we say that I underscore 1, that means I stuck at 1 is detected, and if you say that I 0, then I stuck at 0 is detected. That is what is the notation we are going to follow. Okay. So, so initially just again you see I1 equal to 0 has been given, that part you have to remember. So, if you see that if 0 has been given, so obviously a stuck at 0 will be detected here. So, we write L of I1 equal to I1, that is this list will have detect only one fault for the random pattern, that is stuck at 1. So, that has been written over here. Okay. Now, this one. Now, when you are coming over here, so in this net for the random pattern, what are the faults will be detected? So, obviously stuck at 0 will be detected here. You can also detect the stuck at 0 fault over here. Okay. As well as a stuck at 0 fault will also be able to be detected here, because stuck at 1 fault can also be detected here, that is I1 G1, this line is I1 G1. A stuck at 0 1, a stuck at 1 fault at this net can also be detected at this line. Why? Because you are applying a 0 over here. So, if you are applying a 0 over here, then if this net is stuck at 0, so the stuck at 1, the answer will be 1 and the normal case answer will be 0. Again you are applying a 0 over here, if there is stuck at 1 over here, the value of this net will be equal to 0 in the normal case, and in case of stuck at 1 it will be a 1 over here. So, I1 L of I1 G1, that is this net will be equal to stuck at 1 fault here, this same net, this thing will be here, as well as any stuck at 1 fault will be detected over here. So, this means this fan out, this value will be is propagated here, as well as a new fault is also detected, that is this one. Again for this subnet of the fan out, again obviously this one will be detected over here, because the stuck at 0 fault, sorry, stuck at 1 fault at this net is also detected here, as well as a stuck at 1 fault at this net, that is by I1 G2 1. Okay. This is about stuck at 0 fault is detected because of this random pattern 0. Okay. So, the lists And one more thing we have is obvious, we have discussed many times that a stuck at one fault here is not detected at this line, similarly a stuck at one fault is not detected at this line. Okay, so, it is I2 I1 G1 1 and it is I1 G2 1. So, stuck at one fault here is detected at this net and stuck at one at of this net is detected at this net. So, you see this list is this 2 and this list 1 is this 2. Okay. So, this is what we are getting for the fault list, that is what we are step 1 it is saying that this one. So, it is step 1 is saying that stuck at 1 can be detected at random pattern, this one is telling about this one. So, this is about this one is called this is about step 2. So, step 2 is this one which already discussed about this one, similarly we can get it for this one. So, one for fault deduction one important rule has to be concluded. So, fault detection at Fanout branches. So, what is that? Fanout fault is detected at a Fanout branch, this is the Fanout branch is all faults at the Fanout stem. So, whatever fault list is here, those things you can detect here, that is obvious, as well as stuck at one fault if the signal value of the branch is 0 else 1 else 0. So, it says that, so if this is Fanout branch like this, and so whatever fault list here can also be detected in this Fanout, as well as that along with that you have to make an union of if the signal value is 1, then you can detect a stuck at 0, and if the signal value here is 0, then you can detect a stuck at 1 over here. So, this is the deductive fault simulation rule at the Fanout. So, deductive fault simulation says that all fault at the Fanout stem can be detected and a stuck at 1 if the signal value of the branch is 0, okay, else a stuck at 0 fault will be detectable if signal value is obviously signal is 1, that is obvious. So, this is the rule you have to understand about this. So, deductive fault simulation is all about rules. So, this is a simple rule we have learnt about the Fanout branch. Okay, now, next is, so this is there. Now, we will go to next step, we will see what is the number of faults detected or what are the faults that is detectable at this point. Now, you see, so what happened? So, this is a, so we are applying we have applied a 0 over here. So, now you see, so if it is a stuck at 0 over, so stuck at 1 over here, then the answer is 1, normal case 0, fault case 1. Similarly, for this pattern 1 1 0 1. So, that is we are applying a 0 fault over here, 0 value over random pattern over here, stuck at 1 is fault is in this net. So, signal value is 0 1 0 1 0 normal case 1 fault, same thing here. Here the answer will be 1 0 1 0. That means what? So, a stuck at 1 fault here is also detectable at this line and also detectable at this line. That is why this fault list has I1 1 I1 1. That means what? It shows that for this random pattern a stuck at 1 fault is also detectable by this line and also detectable by this line, right. So, we have this in the list. Next, the same 0 is applied, okay, and say there is a stuck at 1 fault at this line. There is stuck at 1 fault at this line. So, in this case the answer should be 0, fault case it is 1. So, here it is case in this case. So, here there is no effect. So, here it is 0 and here it is a 1. So, you can see a stuck at 1 fault here, this one is also detectable here. Okay. So, this value is also propagated over here. Along with that, now if no fault is in this part of the circuit say. So, now 0 is there. So, you are going to get 0 0. So, here with both of them you are going to get a 1 over here. So, now in this case obviously it can detect a stuck at 0 fault here. So, G1 that is OG1 0. So, that is in this list. So, this list if you observe has now 3 values. One is stuck at 1 is this one, this stuck at 1, this can be detected at this net. Similarly, this net stuck at 0. So, this one is also available here and a new fault we have added is this net stuck at 0. So, this one is added. Similarly, now if you look at this net, so this stuck at fault will be propagated, this stuck at 0 fault will be propagated and finally, a new fault that is a stuck at 0 over here, that is O2 stuck at 0 is added over here. So, now again we can find out a rule for the inverter. So, what is the rule for the inverter? The rule for the inverter is, so whatever fault list we have, this one you just propagate it here because it is detectable, as well as along with that union. So, this list just get propagated here, this list gets propagated here and this is a union. What is the union? If the signal value is 1 in case of normal, then you get a stuck at 0 you can detect, and if it is a 0 in case of normal, then a stuck at 1 can be detected. Okay, in this case as the value is 1, so you can detect this stuck at 0. So, that is what he says. The fault detection of the inverter is fault detected at the output of inverter comprise all faults at the input and stuck at 1 if the signal value is 0 and else stuck at 0. So, that is what we are doing in deductive fault simulation. In deductive fault simulation, what is our idea? Our main idea is that we first start with the fault list in this one, and then when we go from the next level, the next level, the next level, then we have some rules. So, what are these rules? These rules are called deductive fault rules. So, in case of parallel fault simulation, we were doing some bitwise operation, bitwise ANDing, bitwise ORing. Here we are not doing that. Here what we are having? We are having fault list, and then we are propagating the fault list by using some deductive rules. That is, here we are just saying that just propagate the value, whatever can be detected here can be detected in the Fanout branch, along with that add some faults over here. Similarly, for the inverter, just do that and again add the faults over here and add the faults over here. So, this is what is being done. Okay, so, that is instead of doing some bitwise operation or bitwise this thing, here we are having some deductive fault rules. So, those by using these fault rules, we are populating slowly and slowly our fault list which can be detected here. And finally, we will go to the primary output. Then whatever will be the fault list in this case are the faults which are detectable by this random pattern at this output. So, in what will happen in one go, we will be able to find out all the faults which will be detectable by this random pattern. So, we will just see that what is so still now we have seen the rules for this Fanout branch. So, Fanout branches, inverters. Now, we will see for the AND gate, which is going to be very important. So, now what are the fault lists we have? These are the fault lists for this net, these are the fault lists for this net. Okay. And then we have to find out the fault list for this net. Now, let us try to deduce the rules of a okay, this was for the inverter, wait a minute, for the AND gate, yeah. So, we will just have to see for the AND gate. So, this is the list. So, you have to now find out for the AND gate, what are the fault lists for the AND gates or deductive rule for the AND gate. Now, you see, so this is we applied a 0 over here, correct. So, now this is say a stuck at 1. So, if it is stuck at 1 here means normal case 0 fault 1, normal case 0 fault 1, this is what you call 1 0 1 0. So, in this case the answer is going to be a 1 and a 0. So, obviously, this stuck at 1 fault is detectable by this AND gate, correct. So, that is why in this list we are having this one. Now, let us see for the another fault. Let us see for this stuck at 1 fault. So, we are applying a 0 over here. So, it is 0 over here, 1 over here. In this case what happened? We are applying a stuck at 1 over here, correct. So, now it was 0. So, now it has become 1. So, it is 0 1. So, it is 1 0, okay, and in case the answer is 1 0. Okay. So, in the normal case the answer is 1, in the fault case the answer is 0. So, this stuck at 1 fault is also in this list. Okay. Now, let us see the other faults of this other net. That is other part of this Fanout branch. So, this we are applied 0 over here. So, here we are having stuck at 1. So, here it is 0, answer is 1, here it is stuck at 1, that means normal 0 fault 1 1 0, then it is 1 0. So, fault is again detected, right. So, that is I2Z1 is also at this list. Okay. So, now let us see for the fault lists over here. So, now for the fault list over here is this one. So, normal 0 1 0 0, this is 1 1. So, let us see if there is a stuck at 0 fault over here. So, that is on 0 normal 1. So, it is 0 and a 1, again fault, this stuck at 0 fault, because of the stuck at 0 fault, this is 0, in the normal case it would have been a 1. So, here the answer is 1 by the normal case. So, it is this one in the output, and again this stuck at 0 fault is detected over here. Similarly, you can easily verify that if you have a stuck at 0 fault here, this one stuck at 0 fault here, it will be 0 1, again this list will be there. So, all the faults here, here, everything is detectable by this AND gate for the random pattern 0. In the last, if there is no fault in the other part of the circuit accepting the output, that it is a 1 and a 1, and the answer is 1. So, obviously, and the stuck at 0 fault here, that is 1 0 is also detected over here. So, you see in this random pattern what happens, we have detected all these faults and this is a new fault which is added. So, we have to make a rule for the AND gate. So, now let us see, but this is the whatever I have discussed, then you have taken one fault and traversing the whole thing to find out it is detected. Then you are taking a fault and traversing the whole thing to get it detected. So, yeah, so this is not a very good idea of doing it. So, what we have to do is a bit different way, that is by using the rules. Just like what we have found out that, so this is a fault at this net. Now, if it is a Fanout branch, then this will have to be propagated, this will have to be propagated. You need not check whether this fault is detectable by making 0, 1, 1, 0 and all those. Just apply the deduction rules that this one is there in the Fanout branch, this will be propagated. Now the signal value is 0, so stacket 1 will be detected, stacket 1 will be detected. Now as an inverter, the whole thing will be copy pasted over here, and if the value is a 0 over here, sorry, the value, the signal value is 1, so the stacket fault will be detected. Similarly for this case, this whole thing will be propagated over here and this one. That is, you take a case and you then again propagate to the circuit is not a very good idea. But this was only to illustrate. Now you see how can you get it for the AND gate. So for the AND gate, it is very simple to get. Now you can see that our normal signal value is 1, 1. So now in an AND gate, you take the case, this is an AND gate. So if it is 1, 1 and this one. So if it is a 1, we know that this gate is making the gate a pass filter kind of a thing. So if this part is 1, so whatever is happening in this can be reflected over here. This is a very good thing about AND gate, that if this line is 1, then all the activities at this case gets propagated here. Similarly, if this is a 1 and this is a 1, if this is a 1, then also the other case. So if this is a 1, then again all the activities at this point get propagated here. But if it is 0, then whatever happens here, it does not get passed through. Similarly for the other AND gates, other input of the AND gate. That is, in case of an AND gate, in this case, so if this is 1 and this is 1. So if there is a fault or some activity is here, so this can be propagated here and you can observe it. Similarly, as this is also 1, so any type of activity, fault detection, propagation, etc., at this point also will be reflected over here. So it is a very helpful situation when if both the inputs of the AND gates are 1, then what is happening is that, so if this is 1, so whatever is here will be propagated over here. This is because this input is 1. So this, and what do you mean by I11 here? It says that the effect of this stacket fault here, stacket 1 fault is available 1. So this is 1 means the available fault effect of this fault stacket 1 is available here. This for stacket 0 fault effect is available here. And as this is 1, so the whole thing can be propagated over here. So that is why whatever is available over here will come here. Similarly, you also have a 1 over here. Okay? So that means what? Any effect. So anything, any fault effect here will be propagated here, because this is 1. So this 1 here means, that is, this stacket 1 fault, this effect is available here. So this one is there means the stacket 1 fault here effect is available here. Similarly, this one here means this effect of stacket 0 here is available in this. So as this one is 1, so the whole list will be available here. So this thing will come out. Along with that, here the value is, normally in this case it is 1, so this stacket 0 fault will also be detected. So therefore, fault deduction rule for the AND gate with both input as 1 is, all faults at both the inputs, whatever, because when both of them are 1, 1, then what is going to happen? The fault effect of everything, the fault, whenever this is 1, the whole thing gets propagated, whenever this is 1, the whole thing affected. So all faults at both the inputs will be propagated. Along with that, stacket 1 fault at the AND gate, output of the AND gate is detected, because the AND gate here is 1, 1, so this answer is 1, so obviously and the stacket 0 fault will be detected. So this is one rule for the AND gate. This is one rule which you have seen for this AND gate, whenever your input is what you call 1, 1. So now you can easily see, we can just see when this is one rule, when the answer is 1, 1. It is very simple that you propagate this whole value here, you propagate it to the output. Now we are just going to see the 4 cases we have to analyze. Today we will just see one more case, in which case if here the input may be 0 and here the input may be 1. So what is your observation kind of? I think you are correctly guessed. So if says for some reason the signal is 0 over here and the signal is 1 over here, so I think your guess may be proper, saying that whatever list here will be propagated here. That is absolutely true, because this is 1 is there, it will pass everything. But if something is here, some list is here, that cannot be propagated, because this is 0 and it will block the propagation over here. And obviously, so only this list will be propagated, as well as 0, 1 means of an AND gate means what? It is, the answer is 0. So one more stacket 1 fault will be there. So let us just see this before we close. So this is one of this case. Okay. So in this case we are applying 1. Okay. So the answer is 0, 0. Sorry, we are seeing another case which is not 1, 0. So 4 cases we have to see, 1, 1 we have seen, 1, 0, 0 1 will be discussing, that is I told you that whatever corresponding to this list will not be propagated, whatever corresponding to this list will be propagated, okay, and the vice versa for this one, and in case of 0 0 we have to see, so what gets propagated. So, all the combinations we will see. So, if for 1 1 it is very simple, everything gets propagated, for 1 0 the list here will be propagated, and for 0 1 the list here will be propagated, and for 0 0 nothing will be propagated, correct, something like this. But it is not the case. For let us see for 0 0 what gets propagated, and then other case 0 1 and 1 0 are bit obvious as we have seen. So, we will see. So, it is not the case that for 0 0 nothing will be propagated, something will be propagated, we will see, because by logic if both of them are 0 0, then I mean this is blocking everything, then this is also blocking everything, then nothing should be propagated over here excepting only a stacked 1 fault will be detected here at the output, but this is not the case. For both the input 0 0 also something gets propagated, which is interesting to see, and for 0 1 and 1 0 it is bit straightforward. So, that we are going to see in the end. Okay. So, now this input is 1, so here it is 1 1, this is 0 0, so both the inputs are 0 and the output is 0, normal case. Now, you see what happens. So, if it is a 0, so obviously stacked so input is 1 here, sorry, random pattern is input, so stacked 0 fault is detected. So, this thing gets propagated here, this thing gets propagated here, as well as it is 0, so it is 1 1 normal value. So, a stacked 0 fault here and a stacked 0 fault at these nets are detected. So, this is in this list. So, this is the step 1 is for this one. Okay. Now, step 2 says that these are the 2 values at these 2 fan out nets, which is very simple because you are applying a what do you call, sorry, you are applying a 1 over here. So, a stacked 0 fault is here detected here. So, it is again 1 1. So, again stacked 0 fault at this net and stacked 0 fault at these nets are detected. So, this makes list at the level 2 by the what you call this fault deduction rule. Now, from the inversion, so the answer it is 1, it is 0, sorry 1. So, it is 1. So, it is 1 1. Now, it is 0 0. Okay. So, if it is 0 0 means, and it is an inverter, so the whole list will be propagated here, the whole list will be propagated here, as well as stacked 1 fault here will be detected, as well as stacked 1 fault will be detected. So, this is one stacked fault at this net and this one stacked. So, this is the thing which you are going to get, because this is the 2 things at the output of the inverter. So, reductive fault simulation rule of the inverter already we know is what? It is a whole list at the input. Along with that, if it is a 0, then stacked 1 fault at this net and the other and vice versa. So, this is the list over here. Now, we have to find out the step we are trying to reach through is what? This is also a 0, this is also a 0. Now, what is the value at this output of the AND gate? What faults are detected? So, logically I think we should know that nothing should be propagated, correct, because everything is blocking obviously. So, this is 0. So, one stacked 1 fault obviously will be detected over here, that is true. So, OG 3 1 is there, but how come another is here? So, something has been also propagated that you have to check, that is I 1 0 is also here. So, by our logical thinking that 0 is blocking, this 0 is blocking. So, this whole list should be blocked, this whole list should be blocked is correct, should have been there, but still you find out that. So, just let me again see. So, what is there? So, both are blocking. So, this one should be blocked, 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 because this one should be blocked, this one should be blocked, because this whole list is blocked, this whole list should be blocked, because this list should be blocked because this one is 0. Now, this list should be blocked because this one is 0. So, 0 0 the answer is 0. So, at least a stacked 1 fault here should be detected, which is correct. But you see one more element is appearing here, that is I 1 0, that is this stacked 0 fault is detectable here. So, that is one thing which has come, which should not have been come logically, but let us see why it has come. Then we can formulate the rule for AND gate with when both the inputs are 0 0. So, we are applying a 1 over here. So, this is the stacked 0 fault is detected. So, 1 0 1 0, this is the case, this is 0 1 0 1, correct. Now, you see what happens. So, normal case 0 0, fault case this is 1 1. So, now you can see for this fault we are starting. So, the answer is 0 1 and this fault is detected. So, important interesting thing is happening is that and the fault effect is propagated. So, even if the value is 0 0 under the normal case, but still the stacked 0 fault here is detected. Now, one important thing you have to observe that 0 is blocking, this 0 at this input and 0 is input at this one is totally blocking the flow here. and obviously these things are not propagated and these things are not propagated, that is true, but only this thing has been propagated. This is because this fault, this stack 0 fault is affecting both this and it is affecting both the inputs in one go. That is why it is propagating to the output and it is getting detected. So, it is true that this input 0 here, 0 here, that is we have that is for this case of random pattern 1, that is 0 0 1 sorry, random pattern 1. So, it is 1 random pattern 1, this is the random pattern 1, okay, this 0 0. Flow is disturbed. So, these things are not propagated, these things are not propagated, but only these things are getting propagated because this fault is affecting both the lines together. So, the default reduction rule for a 2 input AND gate when both the inputs are 0 is not that nothing is propagated and only a stuck at one fault at the output, it is not the case. Only one more thing will be there, all faults common to both the inputs, because if this is 0. So, one fault which is propagated, which is so it is 0, normal case it is 0. So, a fault case it will be converted to 1. Now, if there is another fault which the same fault which can also convert this one from 1 to 1, 0 to 1. So, the answer output and the answer in the output will be 0/1. So, in that case the fault will be detected. So, let me just put it in the other way before we close for today. So, that is this is 0 0 in the normal case. So, nothing is, so no fault in this net will be propagated and no fault in this net will be propagated, because this is 0, the answer is always 0. But let us think of a fault which can convert this to 1 and the same fault also convert this to 1. So, the output will be 0/1 and the fault can be detected. So, this fault is actually doing the same thing. So, this is actually affecting both these faults, both the inputs of the AND gate together and the fault is getting detected. So, which is the rule for this one. So, we have seen the deductive fault simulation rule for the AND gate under two conditions. If both are 1 1, then obviously the whole fault list from this input and this input should be out, as well as will be here, as well as the stuck at 0 fault will be taken into picture. And for this both the input 0 0, it is very interesting. It is not that nothing will be propagated and only one stuck at one fault will be there, but if there is some fault which is affecting both the lines in common, then that fault will be propagated here, all other things will be dropped and one stuck at one fault will be taken. So, there are two other combinations of AND gate 0 1 and 1 0, which we will see tomorrow lecture. And then what also we will do, we will make a table kind of a thing that will give you the rules for deductive fault simulation for AND gate, OR gate, NOT gate, fan out and all. So, that whenever you have a circuit you can apply the rules and you can go for a fault simulation by deductive mechanism, and in one go you can find out which are the faults which is detectable by a given random pattern in one shot. Okay. Following that we will see the, another fault simulation algorithm in the next class, which will be finishing our discussion. Thank you.